We'll continue the topic. So, Elingham diagram. Elingham diagram is a plot showing delta G against temperature for oxidation. Oxidation means element or metal plus oxygen giving metal oxide. So from this Elingham diagram it is clear that most of the metals, this is for oxidation, most of the metals have negative value. Delta G is negative for oxidation. But our aim is to reduce the metal or remove the oxygen. That means the reverse of this reaction. That means metal oxide is reduced to metal and oxygen. So in this case, most of the metals have positive value for oxidation. So it is not possible to make that reduction spontaneously. So in that case, with the help of Elingham diagram, we can select the reagents or we can select the appropriate temperatures for the reduction of metal oxides. For example, some of the metal, mercury, the value of mercury lies above 0. That means oxidation, it has delta G is positive for mercury at a particular temperature. So in the case of mercury, we can reduce the metal by just increasing the temperature. There is no reducing agent is needed because oxidation is positive. That means the reverse reduction will be negative at that temperature. So all those metals whose oxidation values lies above this line, that means if they have positive value for delta G, we can easily reduce them. That is only for less reactive metals like platinum, mercury, silver, copper, etc. Even for copper also we have to choose a higher temperature of 1200 degrees Celsius. Other metals which are lying below the line, for example, reducing iron. And so we know we have to choose very high temperature for the reduction. That is not possible. Or we can using temperature about 300 Kelvin or 3000 or 5000 Kelvin is not practical. So in that case, we will use the help of the metals or elements which have value below that. That is, we can use them as reducing agents. I will explain with the example. For example, the reduction of iron oxide. We can simply write Fe2O3, we can simply write FeO. Reduction of iron oxide to iron and oxygen. Iron and oxygen. Here the value of delta G is positive. So we will choose a reducing agent, carbon monoxide. Which will undergo oxidation and form carbon dioxide. It's an oxidation reaction, so its delta G will be negative. Then we are allowing these two reactions takes place together in a system or in a vessel. As a result, we are coupling these two reactions. That means we can avoid iron. We can generally write a metal oxide, metal and oxide. We can simply put the values also. If the value of the particular metal is 500 joule and this is 600 joule, then we are allowing these two reaction takes place together. That means metal oxide plus carbon monoxide gives metal plus carbon dioxide. We are coupling these two reactions. So resultant delta G will be minus 600 plus 500 will be 100 joule. That means it is an approximate value, that is not the exact value. That means delta G will become negative, or this reaction will be spontaneous. So some of the metals like zinc iron, that is medium reactive metal, we can reduce using carbon monoxide or coke, or using aluminum, that is called aluminothermy. We can reduce that. But some other metals that is lying exactly below, exactly down in Ehrlingham diagram, they have very high positive value for delta G. We cannot make the delta G for by negative by coupling an appropriate reducing agent. In that case, we will use electricity, that is called electrolytic reduction. So simply we can say that we already learned electrochemical series. I taught you in electrochemistry chapters, that is the reactivity series of metal. The easy way to remember this series already taught in that chapter. You can check that chapter. I will give the link below this. So these metals, that is potassium, calcium, sodium, magnesium, aluminium, etc., we can classify them as highly reactive metals. Then this one, zinc to lead, medium reactive. We can include copper too, medium reactive. Then the last one, that is less reactive. So less reactive metals can be easily reducible by using heat, because their position is high in Ehrlingham diagram. Then medium reactive metals can be reduced using the help of reducing agents. Like, for example, we can reduce lead by using zinc, zinc by using nickel, nickel by using iron, iron by using zinc. But the difficulty is that metal will be more expensive. So less expensive coke, carbon is always used as reducing agent. Then these highly reactive metals like potassium, calcium, sodium, magnesium, aluminum, we cannot reduce using heat, or we cannot reduce using heat and reducing agent. In this case, we will use electrolytic reduction. So this is an easy way to remember the methods which we adopt for reduction. So highly reactive metals will reducing electrolytic reduction. Medium reactive metals will reduce using reducing agent at high temperature, not at low temperature. And less reactive metals directly we can reduce by using only heat. So we have to learn the reduction of aluminium, extraction of iron, and extraction of copper. These three methods we have to discuss in our syllabus. We'll go to that. So third step of metallurgy, we are using the learning, that is called a reduction. Till this time we are discussing the theory which is involved in the selection of reducing agent, that we already discussed with the help of Ehrlingham diagram. Next we are taking examples of reduction. First one, blast furnace reduction of iron. Blast furnace reduction of iron. That is, we are using hematite or magnetite. So blast furnace is a device can withstand very high temperatures. It contains bricks lining inside it. So this is a almost shape of blast furnace. So from the bottom we are passing air at a very high temperature. That is, the temperature here is almost 2700 Kelvin. Then from the top we are adding powdered ore, that is hematite or magnetite. Powdered ore mixed with coke. Coke is carbon which is taken as reducing, not acting, which is taken as reducing agent, plus calcium carbonate which is taken as flux. The reducing agent, and this is flux. So powdered ore is mixed with powdered and concentrated oxidized ore is mixed with coke and calcium carbonate. Coke is taken as reducing agent, it is not acting, that we will discuss, and calcium carbonate is also taken as flux, it is not acting, like that. So these three mixture is put through the top of the blast furnace. So we know that this hot air is moving towards the top. So moving towards the top, the temperature decreases 1500, 1000, like that temperature is going decreases. Due to this high temperature and oxygen, the carbon will burn and form carbon dioxide. But due to the excess of carbon present there, carbon dioxide will combine again with the carbon and forms carbon monoxide. This is acting as reducing agent. Actually, we have taken coke as reducing agent, but the acting reducing agent is the CO, that depends, that is explained by using Ehrlingham diagram. So, the carbon combines the hot air and form carbon dioxide. Due to the excess of carbon, the carbon dioxide here formed again combined with the carbon and form carbon monoxide, which act as reducing agent. Then the hematite or magnetite first reduces to iron oxide and carbon dioxide. Then second step, this iron oxide again combine with the carbon monoxide and form iron and carbon dioxide. This is a reduction. This is the formation of reducing agent. The next one, this at high temperature calcium carbonate, we know that it is decomposable on heating, it is thermally unstable. Calcium carbonate decomposes and form calcium oxide and carbon dioxide. This calcium oxide is acting as flux. Actually, we have taken calcium carbonate as flux, but calcium oxide formed in this process is acting as flux. This calcium oxide, I'll write somewhere here. This calcium oxide will combine with silica, that is a gangue. Calcium oxide is acting as flux. This is gangue and form calcium silicate and form calcium silicate, SiO3, that is slag. It is a low melting, so it will easily deposited on this side, we can remove from this valve. Then the metal formed will deposited below that because of high density, that we can remove from that. Then here the obtained iron will be only 85% pure, because it may contain the impurities, carbon or any other substance like a sulfur dioxide. Volatile will easily form. Carbon dioxide, sulfur dioxide gas, etc. will easily evaporate from this, but the remaining carbon, sulfur, etc. will be remain there. So obtained iron will be only 85% pure. So once again I will explain the blast furnace reduction. The powdered ore is added through the top of, is mixed with coke and calcium carbonate is added through the top of the blast furnace. Hot air at a very high temperature is blown through the bottom of the blast furnace. At the high temperature, this carbon will combine with the carbon dioxide form oxygen form carbon dioxide. Due to the excess of carbon present there, carbon dioxide form carbon monoxide, and that carbon monoxide is acting as reducing agent. Then iron oxide first reduces to iron FeO, iron 3 oxide, it is reduces to iron 2 oxide, then iron 2 oxide again reduces to iron. Then calcium carbonate, it is thermally unstable at the high temperature, it will decompose and form calcium oxide and carbon dioxide. Calcium oxide, it is acting as a flux combined with the gangue, that is sand, silica present there and form calcium silicate. It is easily fusible and low density. It will separate above iron in the below of the blast furnace. The formed iron will deposit at the bottom of the blast furnace due to its high density. There are two valves are placed for that. From these valves, the low dense slag will be separated, and the bottom valve we can separate the iron. The obtained iron will be only 85% pure. Then we have to, the last step we have to refine the iron. Next, next class we will discuss with the reduction of copper and aluminum. Copper is extracted from copper pyrites or copper glands. IDCUFES2. It is first froth flotation process. During using froth flotation, it is purified. Then using roasting, it is oxidized. During the roasting process, it is done in a decimer converter. It's a very high temperature withstanding vessel. On heating, we doesn't want the diagram. On heating, what happens is CuFeS2 is decomposed first to CuS and FeS. Then second step, CuS is converted into CuO. FeS is converted into FeO. Then we are continuously heating, then we are not adding any reducing agent here. We already discussed copper is less reactive. So during this process in Bessemer converter, during this process what happens here is, this copper oxide formed will combine with the remaining copper sulfide and form copper and sulfur dioxide. Actually, here what happens, we can say it is self-reduction due to high temperature. It will undergo self-reduction and form copper and sulfur dioxide. But in that converter, copper will be in molten form, and this sulfur dioxide is escaped through this molten copper, produce blister on drying, on solidifying, it will form blisters like so many blisters in copper block obtained. So the obtained copper is called blister copper. So the extraction of iron will copper is very easy. The copper ore is froth floated or is roasted in a Bessemer converter. During the Bessemer conversion process, it is heated with oxygen at a higher temperature. First it will decompose CuS to CO, FeS to FeO. Then it will undergo self-reduction. Some of the remaining copper sulfide will combine with the copper oxygen and form copper and sulfur dioxide. Then we have to remove these impurities. Here iron oxide is impurity, so we'll add silica as flux. They will combine and form FeSiO3, that is easily fusible and separated at the top of the metal. We can wipe it out. So this is a process which are used for the reduction of copper pyrites. The same way we can discuss the aluminum. In the case of aluminum, so we are discussing three examples. First we are using reducing agent, second by using only heat, third one by using electricity, that is called electrolytic reduction. Due to the high reactivity of aluminum, it is very easy to use electricity than other methods. If you are using other metals as reducing agents, that will be more expensive than this method. So in this, a device contains, a vessel contains carbon lining. Carbon lining is act as cathode, and a series of carbon rods is act as anode. Then it is connected to a source, electrical source. And the molten ore, we are using alumina, is bauxite. Al2O3 XH2, on heating it will remove the all water and we will get Al2O3. It is called bauxite. That is pure ore of aluminum. It is mixed with cryolite Na3Al(F6) to reduce the melting point. So we can easily melt the ore. Al2O3 is mixed with cryolite. There are two reasons for mixing with cryolite. When we mix with cryolite, it will reduce the melting point of the ore and it will increase the conductivity of ore because of the presence of iron. So during during applying electricity, the aluminum, it contains Al2O3 contains Al3 plus ion. It will move to the cathode and accept 3 electrons and get reduced and deposited here, and we can separate it by using a valve over here. Then the oxygen will move to the anode. There are carbon rods hanged and dipped into this solution. It will combine with that and carbon dioxide gas is evaporated or liberated at the anode. So after some time we will get pure aluminum. In this process there is no such impurities present because of the, we know that due to the reduction potential only particular metal will reduce there. So we will get pure aluminum here. So metal which is obtained using electrolytic reduction, there is no need of further refining or purification because it contains pure metal. So here a vessel which is lined with the carbon is acting as cathode, and a series of carbon rod is hanged and dipped into the solution is acting as anode. Then the ore is mixed with cryolite and electricity allowed to fall through, pass through it. During electrolysis, Al3 plus move towards cathode and accept 3 electrons and undergo reduction and form metallic aluminium, and oxygen migrate towards carbon and undergo oxidation, so combine with the carbon and form carbon dioxide. It will liberate it. So after some time we have to replace these carbon rods because it will react and consume and it is used up. Then cryolite is added to Why we are adding cryolite? To increase the conductivity of the solution and to reduce the melting point. Then next class we will study about, next section we will study about the last process in metallurgy, that is called purification or refining of metals. That is the last process in metallurgy.